I have to switch to that for the time being. Okay, so let me know if you're able to see my screen. Is it visible? Is my screen visible to everyone?
Yes, sir.
Okay, so we're going to talk about in today's class. One moment. Probability and statistics. Okay. So before we begin, some basic definitions because so that I want everybody to be on the same page. So you all know what I'm talking about. So I'll start with by introducing you all to some basic definitions which I'll be using again and again and again. So first, let me write down those terms which I'll be defining very soon. The first term is what we call as trial. The next quantity is the next concept or the next idea. Next definition is an outcome. Next one is a sample space. Then we have an what we call as an event. Okay, so these are the quantities that I'd like to first define. So what exactly is a trial? I'll give an example so that you all understand this. So what is a trial? A trial is, simply put, it is a single performance. It's a single performance of an experiment. Okay? Single performance of an experiment. In other words, a trial is a single reading. Okay? A single performance. When you perform the experiment only one time. Okay? Or in other words, a single reading. Performing an experiment only once, that is called as a reading. So a single reading is what we call as a trial. Then what is an outcome? An outcome is when you perform a reading, when you perform the experiment once, what kind of outcomes, what could be the results that you can get? Okay, so each possible result is an outcome. So each possible result of a trial. Okay, then we have the trial. Trial is a single reading. Every time you do a trial, then you're going to get lots of different results. All these, every possible result, that is an outcome. Then, how many different such outcomes can you have? Okay, all of these outcomes, if I put them together in a set, okay, that is called as a sample space. So, a sample space is the set of all possible, the set of all possible outcomes of an, the set of all possible outcomes of an individual trial. Okay, so that's the sample space. Then what is an event? An event is sample spaces. So let me go through it one by one. So first we have a trial, which is a single performance of an experiment. If it's not making any sense to you right now, don't worry. I'll give you an example. You'll understand this very soon. So a single performance, you perform the experiment only once. That is a single reading. That is what we call as a trial. Then when you perform a trial, then what is the outcome that you get? Okay, so every such possible outcome, every such possible result is called as an outcome. Now, because a single trial can give you only a single result, or a single trial will give you a single outcome. But what are the different possible outcomes? All possible outcomes. So you make a set of all such possible outcomes that is known as the sample space. And finally, we have what we call as an event. So what is an event? Event is a subset. Event is a subset of the sample space, okay, which satisfies certain conditions. Okay, so we have these four basic definitions that we start with. A trial, which is a single like a single reading. The outcome of a trial, okay, the result of the trial, which is called as an outcome. All possible outcomes, which we call as a sample space. And from these all possible outcomes, let's say you take a small subset of that, that is called as an event. So these are the four basic definitions that I want you all to remember. Okay, because if you know these, then the rest of it becomes really straightforward. So let me try to explain all of this using an example. I'll use a very simple example, an example that you all are already familiar with. Let's say I take the example, the tossing, the rolling of a rolling of a pair dice. Okay, so let's say I have a pair dice. What is the meaning of this word? Why do I say pair dice? That means that dice that is an equal possibility. When you roll it, any one of those six outcomes are possible. Okay, so it's fair. So any result is possible. That's why it's called as a fair dice. Okay, so if you want to, let's say, roll a dice, okay, every single go. So this is how a dice looks like. So it is in the shape of a cube. Okay, so you'll have different markings here. Let's say you have here one here, and then two here, and then you have three, and so on. Okay, so this is how the fair dice looks like. And then you roll this dice. Okay, uh, every single roll, a single roll of the dice. Okay, a single roll of the dice. Let's say you roll the dice only once. Okay, a single roll of the dice. Like I said here, what is a trial? Trial is a single performance of an experiment or a single reading. So when you roll the dice a single time, only one time, okay, that is called as a trial. Okay, a single roll of the dice, that is a trial. Now, when you roll the dice only once, okay, let's say you get the output, okay, you get some result here. Let's say you get a 5. Okay, when you roll the dice once, the answer that you get, the result that you get is something like this. You don't get 5. What you get is a pattern of dots. That's what you get. So let's say you get something like this. Okay, so this is the result of a single roll of the dice. Okay, so this result, this is called as an outcome. When you roll it only once, and what you get, okay, let's say you get something like this, that is called as an outcome. Is this clear? Now let's proceed. Okay, so now so we understood what is a trial, then we have understood what is an outcome. Then coming to sample space. All right, is this the only outcome that is possible? No, there are other outcomes also possible. So what are the other outcomes? The other outcomes could be any of this. So let's say, let me just quickly draw this, the other outcomes. So let's say this is the face. By outcome, what we define is the pattern of dots that you see on the top of the dice. That's what we call as the result or the outcome. Okay. So we have, because a dice is a cube has got six faces. So each of the six faces will have a different pattern of such markings. So one face will have a marking like this. Another face could have a marking like this. Another face could have a marking like this. Yet another face will have a marking like this. Another face will have a marking like this. And the last face will have a marking like this. Now remember, we are not talking about the numbers here, okay? We are just talking about the patterns that you get. When you roll a dice, what do you get? Okay, so these are the six different possibilities that you can have. The pattern that you see on the top of the dice, it could be any one of these six. Is that clear, everyone? So let us say I create a set. Okay, a set, as you know, what is a set? Set is a collection of items, right? So let us say I take all of these six outcomes, okay, all of these six outcomes, and I create a set. Okay, so which means now if I roll any dice in the world, any dice, any pair dice in the world, if I roll it, then what will happen is I'm going to see any one of these six patterns, right? Roll any dice in the world, you are going to see any one of these six different patterns. So this entire set of six different patterns, this is called as a sample space. Okay, is this clear?
Yes, sir.
Okay. So we have understood what is a trial, what is an outcome, and what is a sample space. Okay. Now the next thing that we need to think about is what is an event. Event is a subset of a sample space. Remember, we are talking about a subset. What is a subset? You see, sample space is a set and event is a subset. Now, from your knowledge of set theory, okay, your basic knowledge of set theory, what do you understand by this? What is a subset? What is a subset? A subset is if, let's say, I have a set, a collection of quantities which are there inside this. Then from here, let's say I take a smaller number of items from here. Then what we have here is this is the subset. This blue, whichever I have drawn in blue, this is the subset, and whichever I have drawn in white, that is the set, right? Or it is also called as a superset, right? So now, what is an event? Event is a subset. Okay, understood? So it means any one of these, any subset, it could be, and so it could be something like this. Let's say I create a subset like this. Okay, let's say I create a subset which looks like this. This is one subset. Then I could create another subset like this. Just give me a second. I seem to be getting a phone call. One moment. Okay. Okay. So you can see here, do you agree that these are all subsets? Let's say this sample space, I refer to it as the set S. This sample space, I call it as the set S. Let's say this is the set A, and this is set B. Now, do you agree that A is a subset of B?
Yes, sir.
Yes. So A is a subset of B. I think this. Sorry, A is a subset of S. And what about B? B is also a subset of S. Correct. So because these elements they are included in this. So this is both of these are subsets. Now, uh, what is how do we know which are the elements? How can we judge them? Yes, we can. Because you see, when can we call a subset an event? When can we call it? We can call it an event if it satisfies a certain conditions. If there are certain conditions which are satisfied by the event by the subset, then we can call it as an event. So here, what are the what is being which condition is being satisfied by this subset A. So here A is basically the set of uh, maximum or minimum markings. Okay, the set of minimum, maximum or minimum markings. Does that make sense? Because you see, what is the minimum? If I ask you a question, what is the minimum number of markings? One marking. What is the maximum number of markings? Six markings, right? Six dots. So either one or six. So the set of all maximum or minimum markings. Okay, that is your set A. What about set B? How do you? What kind of condition does it satisfy? Set B. What kind of condition? Okay, make sense? Does this make sense?
Yes, sir.
Mhm. So you can see here both of these A and B, both of these A and B are subsets of S. Okay, so both A is subset of S and B, which is also a subset of S. Okay, both A and B are subsets of S. Okay, and also both A and B satisfy certain conditions. Okay, so by definition, a subset of the sample space which satisfies certain conditions, these are called as events. So in this case, both A and B, both of them, okay, both of them are events. Is that clear, everyone? Both A and B are events. Understood, everybody? Any questions?
Yes, sir.
Okay. So this, it's very important that you keep this in mind. Okay, please try to understand this. If you have not understood this, watch the recording again, so that this becomes clear. It's really important that you get this concept clear because much of what we are going to discuss later on, I'm just going to keep on using these terms. Okay, so trial, outcome, sample space, and event. These four basic things you all should know. All right. Okay, so now once this is clear, once you start thinking about this, now you can note one thing. I have not used numbers, right? I could have just chosen one, two, three, four, five, six. I could have just chosen like this, no? For to me to define the sample space, but I did not do that. Why is that so? It will become clear very soon when we discuss what is called as a random variable. Okay, so I'll come to that a little bit later. Right now, just focus on what we have over here. So we have basically a sample space, and remember, sample space is a set. A set can be anything. It need not only be numbers. A set can be anything. A set can be human beings also. You all are a set of students. A set can be anything. So here, what is a set? Set is the design that I see on the top face of the dice when I roll it. That's how I define as the set. And when I define this sample space in this way, then there are six possibilities. So that means there are six possible outcomes in the sample space. And if I roll the dice once, that is, if I perform one trial, then I'll get one of these six outcomes. All right, everyone? Okay, so now let's proceed. Next, we're going to talk about an important device which is called as a Venn diagram. Okay, a very important concept called the Venn diagram. You might have already come across this Venn diagrams on the internet. You know, in terms of memes, you can just search. Lots of memes are available on the internet. Venn diagram memes. You have probably seen something like this. They're very common words like yeah, something like this, right? Yeah, some yeah, lots of inappropriate jokes also you will get. So you have probably seen something like this on social media, right? So these are basically Venn diagrams. Okay? Modi also seems to have come over there. All right. So you can just watch this. You can have a lot of fun here. Okay, just look for Venn diagram memes. Okay, so this is basically a Venn diagram. Okay, so what I mean by that is we need this concept of the Venn diagram. It makes understanding different concepts of fact theory becomes very easy. So what exactly is a Venn diagram? So what is a Venn diagram? It consists of a rectangle. This is a graphical representation of the set. Okay, and what is the purpose of this rectangle? The interior, the interior of this rectangle represents the sample space. Okay, so a Venn diagram basically it consists of a rectangle whose interior represents the sample space. Okay, then what is there inside the rectangle? And inside the rectangle, you could have one or more closed curves. One or more closed curves. And what is so special about these closed curves? Because the interior, whose interior represents an event. Okay, so we have a rectangle, and the interior of the rectangle it represents the sample space, and inside this rectangle we have closed curves. The interior of the closed curve it represents an event. So let me take an example here. So let me draw a rectangle. I'll take the same example as earlier, the example of the rolling of a dice. Okay. Okay, first, before going to that particular example, let me first clear up certain definitions here. So this is the rectangle that we're talking about. This a rectangle, it represents the sample space S. Okay. Now inside this rectangle, we could have, one or more closed curves. So you could have a closed curve like this, just like we saw some time back. Okay, when you search for Venn diagram mean, so you could have a closed curve like this. Let's say this closed curve, I call it as A, and another closed curve. Let's say this closed curve, I'll call it as B. Okay, let me mark certain regions here. Region number, this region number 1, region number 2, region number 3, and this last region number 4. So these are the different regions. Okay, now What is so special about these regions? So first, let me say here, S is the sample space. S represents the sample space, and A, comma B, these are two different events. Okay, A and B are two different events. Okay, so now we have these different regions. Okay, so what do these different regions mean? So first, let's talk about the region number one. What is region number one? Region number one is it contains all the set of outcomes. Region number one, because after all, this is also a set. It is also a subset. Region number one. So region number one, it contains outcomes, outcomes belonging to A. Okay, region number one, first of all, it contains outcomes which belong to A, but not to B. Okay, this region number one, this region, it contains all the outcomes which belong to this event A, but not to this event B, because B is this part, right? We are not, B is this entire region, right? So it does not include even one outcome which lies inside B. Okay? So region one contains outcomes belonging to A but not to B. Now region number two. What about region number two? Can anyone tell me? What will be the contents of region number two?
Contains the outcomes belonging to B.
Contains the outcome belonging to
To B,
B,
not to A.
but not to A. Okay. What about region number three? This also contains outcomes belonging to region number
To A
three,
and B.
both, right? Both A and B. And finally, region number four. What does region number four contain? It also contains outcomes. What does this contain? Region number four. Region number four is outside A and B both, right? That means it contains outcomes neither to A nor to B. Everyone understood? So we define these different regions like
Yes,
this.
sir.
Okay. So this region, so we have, we can define certain operations based on our understanding of whatever we have seen over here. We can, define certain kind of operations over here. But before that, let me define one more kind of a set, which is called as, let me do that here, because that concept becomes very important later on. That's called as a null set, which is usually represented by a phi, which is a null set. Null set is the event. Null set is the event which contains, anyone? What is a null set? It's an event which contains no outcomes. It's something like the zero. Okay, zero is a number which does not have any value. That's one of the biggest contributions of India, right? Only Indians can come up with something like this, which adds value but does not carry any value in itself, right? Only Indians can come up with certain things. No wonder we Indians, we use like how we use missed calls for conveying information, right? If you reach home safe, give one missed call. If you're in trouble, give two missed calls. A missed call does not carry, it does not have any value on its own. It's zero. It does not cost you anything. But still, we can find some use to it to give some value. Okay, that's a silly example here. But basically, a null set is like a zero. Okay, it's an event. It is also an event which contains no outcome. Just like the zero. Zero is also a number. All numbers carry value, but zero is a number which does not carry any value. Okay, so that's a null set. As opposed to null set, we could have another event. Instead of no outcomes, it will contain all outcomes. Do you know what this set is called? The set which contains all the outcomes. What is it called? It starts with U. It's a universal set, which is represented as the capital letter U. All right, everyone? Okay, so now let's define certain operations. Operations on events. Okay, so first operation is an intersection. How do you define an intersection? What is an intersection? So let's say I have two events, A and B. We represent their intersection by using this symbol. Okay, A intersection B. Okay, so what is an intersection? Intersection, it is the event comprising of outcomes the event comprising of outcomes, sorry, not outcomes, of all outcomes that belong to both A and B. Okay. So here, which is the intersection? All the outcomes which belong to both A and B. Region 1, 2, 3, and 4. It is region number 3 because that's the only the region which contains outcomes belonging to both A and B. So here, region number 3 here. Okay. So that's for what is called as the intersection. Next, what about union? Can anyone tell me what is a union? Let's say A union B. Okay, yes, let me just graphically show you what this intersection is. So let's say I have an event A and another event B. So event A and event B. So intersection will be this overlap region. This is the intersection of A and B. Okay, what about union? What is a union? What is a union? How do you define it? The event comprising of all the outcomes yes anyone
Belongs to A or B or both. Yes, sir.
yes that belong to either A or B okay or both okay? It's understood if I say A or B it's understood that it could be both of these okay so if let's say I have this to be again just like before event A and event B so they have some kind of overlap here so event A and event B then the union of A and B will be all of this events which exist which are okay let me write down just to make it more clear okay, A or B or both yeah. So the events the outcomes which belong to A the event which contains the outcomes that belong to A or which belongs to B or which belongs to both so this is your A union B right so that's your union right then we have another definition that is called as a complement. For complement, you don't need two events, you just need one event only. So let's say I have an event A and I want to find its complement. So how do you find out the complement? So event A, to find its complement, you just put a bar on top. Okay. So what does this complement mean? It means uh, the event comprising of all the outcomes that do not belong to all the outcomes which do not belong to A. Okay, so that's what is meant by a complement. So let me draw this here. So let's say for that, of course, I need the sample space. So let's say I have the sample space here. So this is the sample space S, and inside the sample space, I have an event. Let's say A. This is the event A. Then the complement of A will be all the events which are not included in A. So this is complement of A. All right, everyone. So now certain results that you can obtain from here, interesting properties. These properties are, first property is, if I take the intersection of A with its own complement, if I take the intersection of A with its own complement, what will I get? I want you to think about this. And if I take the union of A with its own complement, what will I get? I want you to think about this. What do you think? Intersection of A with its own complement and intersection of A and union of A with its own complement. What will I get? Any idea? Anybody? A intersection A complement. No one? What is A? A is the events which are contained inside this, right? And A complement is which are not contained in this. So what is intersection? What is common between these two? Nothing is common between these two. Yes or no? Because complement is events that that do not belong to A. So there is nothing common between A and A's complement. So what will the outcome be? If you take the intersection between two sets which do not have any common things at all, what will I get? You will get an event which does not contain any outcomes. An event which does not contain any outcomes, what is it? That's the null set. Okay. Now what about A union A complement? A union A complement, what will happen is A and it's A complement. A is what is there inside and A complement is what is there outside. If I take the union of this, it will give me the sample space. Two important results. Okay, we'll be using this. You will be using this, maybe if not in this course, then another course on research methodology where there is a section on probability and statistics. There's a module. So over there, that will be in the third semester. Over there, you will be using these results very frequently. All right. Then another result. What is this? This you'll find one more concept. What is A minus B? Okay. What is A minus B? A minus B is defined as the outcomes, the event comprising of outcomes in A that do not belong to D. Okay, I think I should do this as the difference. This is the difference between two different events, A and B, A minus B. So this is the event which comprises of all the outcomes which belong to A but do not belong to B. Okay? So graphically, if I were to express this, it could be something like this. So let's say I have one event A and I have another event B, A and B. So A minus B means all the events which comprise of outcomes that belong in A and do not belong in B. It means these are the set of events. These are the set of outcomes. This shaded part, this is your difference. So A minus B. Okay, because you can see here any outcome if you consider in this shaded region, it contains specifically it is specifically in A and it is not in B. Even you cannot take any outcome in this overlap region because that would mean that it lies in A as well as B. That is not allowed. So A minus B is which is lying only in A but not in B. So that's the region that we have here. Okay, is that understood? So we can write this in this way. Okay, A minus B is the difference. Okay, so this can be written as A minus B can also be written as A intersection B's complement. Does that make sense? Can you see how? It will become clearer if you look at the sample space. Imagine the sample space which encloses both of these. Okay, both A and B. Like this. This is the sample space. Can you see how A intersection B complement? Because what is B complement? B complement is anything which is not there in B. Okay, which is everything else. Okay, and what is A intersection B complement? A intersection B complement is the common elements, the common outcomes, the outcomes which are common to A as well as everything that is outside B, which is exactly the space that we're looking for. Okay, so that's the event. Is that clear, everyone? Yeah, and before I forget, one more thing that I'd like to show over here. This A's complement can also be written as can the A's complement, the complement of an event, be written as complement of A is equal to sample space minus A. Make sense, everyone? Sample space minus A. Again, what is the difference? Event comprising of outcomes in A that do not belong to B, right? Here, the first set is S. So, event which contains outcomes that belong to the sample space but not to A, which belong to the sample space but not to A. That is nothing but your A complement. Okay, so you can write down this complement in terms of the difference, and you can write down this difference in terms of the intersection like this. All right, everybody. So here we can see very easily how can you write down region one, region number one. I would like to leave it up to you. You can see this region number one. Okay, what is this region number one? Region number one is nothing but A minus B. Can you see that? Region one is nothing but A minus B. Is that clear, everybody? The outcomes which are contained in A but not in B. That is the region number one. Similarly, the region number two, the outcomes which are contained in B but not in A. So what will that be? B minus A. Is that clear? Okay. Then region number three, which contains the both outcomes which belonging to both A and B. Belonging to both A and B means we are talking about the intersection. So this is nothing but the intersection. A intersection B. And region number four, how do you write region number four? Region number four, the outcomes which belong neither to A nor to B. How do we write this? Neither to A nor to B. Can we write it like this? Okay, so I'll leave it to you to verify for yourself if these are indeed the relations, the correct relations over here. Right? Are there any questions so far? Any questions? Now let's take an example. Example is okay. Let me a six-sided dice is thrown. Six-sided dice is thrown. Let A be the event, sorry, not set. We are using the word event here. Let A be the event. And how do we define as event, which is defined as let A be the event which is defined in this way. Number divisible by 2. Let A be the event which is defined as number divisible by 2 and B be the event B is the event which is defined as the number divisible by 3. Okay. Question is, draw the corresponding Venn diagram. All right. So I think it's better that I leave it to you as a homework for you to practice. Can you all do this? Can you all do this? On a roll, a six-sided dice is thrown. A is the event which is defined as number divisible by 2 and B is the event defined as the number divisible by 3. You have to draw the corresponding Venn diagram. Can you all try this? All of you? Yes? No? Any response?
Yes, sir.
Okay. Then the concept of subset, you already know what a subset is. All right, so now let's look at some of the identity operations, okay? Some of the identities of the union and the intersection operations. Important to know some of these terms. Identities of the union and the intersection operations. All right. The first operation is what we call as the first identity is what we call as commutativity. What is commutativity? Can anyone tell me? What do you understand by the word commutativity? Or to commute, the meaning of the word to commute. What is the meaning of this? You have done this in your quantum mechanics, right? You have learned commutator brackets, correct? All of you? Yes? No? If you don't know, I can tell you about this. Commutativity. Anyone? What is commutativity? Or what do you mean by to commute? You did this in quantum or not? In quantum mechanics? In quantum mechanics, this one. The X operator and the P operator. What is the output? The X operator and the P operator. When you do the try to find out the commutator bracket of X and P. What is the output? Anyone? The commutator bracket. Yes? No? Do you know this or you don't know?
Sir, IH cross.
IH cross. Good. What does that mean? You know the answer, right? You know that the answer is IH cross. But what does this mean? What is the physical meaning of commutator bracket? What is the physical meaning? This result that it is equal to IH cross, what is the physical meaning? Anyone?
Sir, if the answer is 0, then the two operators commute. But if it is not, then it doesn't commute.
Okay, but you have just given me the definition of commutation. Okay, I want physical meaning. Physically, what does this mean? What you said is correct only. Okay, but you have just given me the definition of the commutation, the commutator bracket operation, right? You say if it is 0, then we say it's commute. If it is non-zero, then we say it does not commute. Now, what I'm asking is, what is the meaning of the word when I say it's to commute or
So they
when
have the same eigenfunctions.
okay, all right. But that again does not answer my question. You're giving my answers in mathematical terms. Do you realize? I'm asking you the physics. Physical meaning means what is the physics behind this? What do you understand by this? Okay, what is the physics that is happening over here? You are giving me mathematical definitions. Because you remember, at the end of the day, all of you are physics students. Okay, don't get lost in the mathematics. Always try to find out what is the physics behind it. That's why we always ask this question: what is the physical meaning? Anybody? Any idea?
So they can be measured simultaneously.
It can be my really? No. Okay, let's go to a definition of the commutator bracket. What is the meaning of the commutator bracket? Suppose I have an operator A, right? A, comma B. Let's say. How do you define it? How do you define it? It is, you would have learned, no? It is AB minus BA, right? This is what you have learned, right? This is the definition of the commutator bracket. Is that correct? This is how you have learned the definition of commutator bracket. Yes? No? Or you have learned something else?
Yes, sir.
But actually, this is not correct. Okay? You see, what are these? These are operators. You have to keep in mind that these are operators. Okay? Operators on their own, they do not have any physical meaning at all. Operators will have physical meaning only when they operate on something. Only when we get some kind of a result out of these operators. Only then they will have some physical meaning. Okay? So when I say A commutator B, commutator bracket of A and B is equal to AB minus BA, it is absolutely garbage. Okay? What you have to say is when this commutator bracket, this is also an operator, when this operates on, let's say, some function, okay, that is equal to AB operating on this function minus BA operating on this function. Okay, and what is the meaning of AB operating on this function? It means first you operate B on this function, then you operate A on this function. This is the meaning of this. Okay, because operations, they always move from left to right. And here, what does this mean? It means first you operate A on this function, and then you operate B on this function. Okay. So when this result turns out to be 0, what does this mean? It means when it is 0, it means it does not matter. That is, it does not matter whether one operates A first and B next, or vice versa. It does not really matter. That's what it means, no? Because if it is 0, then from here you can get, if it is 0, it means A operating on B operating on B must be equal to B operating on what A has operated upon. Make sense? You can see here, the order does not matter. First, I have operated B, then I have operated A. Here, I have applied the operator A, then I have applied the operator B. The order does not matter. You can operate them in any order that you want. So to commute, physically what this means is the order of appearance does not matter. Is that clear, everybody? Is that clear? So what is the physical meaning of this? When I say xp is equal to I h cross, what does it mean? It means if I first operate p, the operator p, okay? If I first apply the operator p on some wave function, okay, and whatever result I get, I operate x, okay, and I do vice versa. I operate the x operator on psi, and then whatever result I get, I operate p on that. These two are not equal. Okay, the order in which they appear, the two operators, the order in which they appear, that order really matters because it is not zero. Okay, that means the meaning of that is the meaning of it does not commute. The order of appearance, it does matter in this case. So x and p operators, they do not commute. To commute means the order does not matter. Make sense, everybody? Is this clear?
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
remember this, okay? Don't get lost in the maths, okay? Always keep the physics as your focus. The maths is just a tool, okay? Just a tool for you to understand the physical reality, but the maths does not become the physical reality. Never consider the maths to be the physical reality. You can talk about eigenfunctions and eigenvalues and so on, but until and unless that has got some physical significance, that is totally meaningless, all right? Okay, now coming to commutativity. So here again, the union and the intersection operations, they are commutative. So what that means is their order does not matter. So when I say that two operators, the union and the intersection, they are commutative, that means the order does not matter. Okay, the order of appearance does not matter. Okay, so if the order of appearance does not matter, what does that mean? I have, let's say, intersection. Okay, I have the intersection here. And on one side, I put A, on the other side, I put B. Okay, so this is, I have applied this in this way. Okay, when I say commutativity, what it means is the order of appearance does not matter. Okay, so I could swap the side. I could put B in front and I could put A behind. The result will be exactly the same. Is that clear, everyone? Likewise, if I have A union B, same way. In this case also, if I have A union B, in this case also, I can change the order. I can swap them, the order of appearance, because they commute. The order of appearance does not matter here. So this also will be the same. Is that clear? Is that clear, everyone? Can you tell me if the vector dot product, is it commutative? The vector dot product, is it commutative? The vector dot product, is it commutative? Yes, it is, because A dot B, vector A dot vector B is equal to vector B dot vector A. Does not matter A and B in which order they appear. But what about the cross product? Is it commutative? A cross B, is A cross B equal to B cross A? No, it's not. So the cross product is not commutative. All right. Then next we have associativity. Associativity means it does not matter which event you associate with which. Does not really matter. So let's say intersection. So I have, let's say, three sets A, B, and C. And let's say I put a intersection operation in between. Okay. So now when I do this, now there is a confusion. Which do I take? Because intersection is a binary operator. That means it has to operate on two operands at a time. So which one do we take first? Do we do this? The question is, when I say A intersection B intersection C. So question is, do we first use the bracket to show which is done first? So do we first do B intersection C and then do A intersection, whatever is the result? Or do we first do the intersection of A with B and then whatever result we get, you take the intersection with C? The associativity means that does not matter again. Okay. Same thing holds good for union also. So we have A, B, and C, and then we have in between we have the union operations. Like this, likewise in this case also, let's say I would like to know whether we can change the order. So first, how do we not order, whether we can associate this first B intersection C and then B intersection with A, or first A intersection B and then intersection with, sorry, A union B and then union with C. Again, in this case, does not matter. That means both the union and the intersection operators, both of them are associative. All right. Then the next identity is what we call as distributivity. Distributivity means I can, if I have, now let's say mix the union and the intersection. Okay. So let's say I have A two different operations A and sorry, two different operations, union and intersection, A, B, and C. So this is what we have. And then let's say I use both the intersection as well as the union, both of them I do. Now here, let's say I decide that, first I'm going to do the union and then do the intersection. What the distributivity it says is, when you're trying to do this, when you're trying to apply the intersection on a union of two sets, that is the same as applying the intersection first on on both of these and then taking the union. Okay, that is the distributivity. So it is the same as taking the intersection of A first with B, okay, and the intersection of A again with C, and then follow it up with a union, whatever first I was originally trying to do. So that's the distributive. Same thing also again holds good for the other way around also. So if I have A union, let's say B intersection C, this is the same as first you take the union with B and C, A union with B and A union with C, and this result you take the intersection. So that's the distributivity identity. Clear, everyone? And then the final identity is what we call as idempotency. What is idempotency? It basically says that if I take, it basically idempotency is got to do with the identity of an event. Okay, so let us say I have the union or the I take the intersection or the union of A with itself. Okay, A. If I take the union of A with itself, I will get back A. So you can take the union of A with itself as many times as you want. You'll get the same result. Similarly, if I take the intersection of A with itself, then you'll get that. So these are some basic identities of the union and the intersection operations. Is that clear, everyone? One small result. Let's try this out. Let me show this. Okay. Show that A minus B, we have to use all the results that we know, A minus B union A intersection B, this is equal to A. This is what we have to show. Okay, the result is very straightforward. So here the solution, for the solution, very straightforward. So here we have A minus B, and we already know, we saw sometime back, minus, how do we define it? The difference between these two, it is simply difference between these two is defined as A intersection B complement, right? So A minus B is A intersection complement of B. Okay, so this is what we have. So now we substitute this back over here. So therefore, in this, so this is what we get. So this one, this is equal to, so A minus B, will replace it with A intersection B complement and union of that with A intersection B. Okay. Now, can we use the distributivity property? Yes, we can, right? Because you can see here, this what we got over here is the same as this A intersection B union A intersection C. You pretend that this is B and this is C, right? It's the same thing. So this by distributivity property, we have A intersection B complement union B. Okay. We have just used this first distributivity property. So as a result, what is B complement union B? What will that give us? Union of a set with itself. What does that give us? Union of a set with itself. Union of a set with its complement will give you the sample space. Union of an event with itself. So B is an event, and B complement is the complement of that event. So event and its complement. You take the union. This is going to give us the sample space. So as a result, we have A intersection with the sample space. What will A intersection with the sample space give us? If I take the intersection of A with its own sample space, okay, I did not mention here A. If I take the intersection with the sample space, it will give me A itself. Okay? I leave it to you figure out how this is really straightforward. So this is going to give us A. So this is true. Okay. Another question, which I'll leave it to you as a homework. This will be your homework. Show that A union A intersection B, A union A intersection B is also going to be equal to A intersection A union B, and this will be equal to 2. Can you try this? Really straightforward. All right. I'll give you a hint. You have to use the distributivity and the idempotency properties. By the way, I don't think these are the properties. My mistake. These are the properties of the union and the intersection operations. Okay. And finally, we have what is called as the De Morgan's law. De Morgan's laws. Write this here. De Morgan's laws. There are two parts to this law. The first part is it's got to do with union, the complement of unions and the complement of intersections. So suppose I have A and I have another event B, and I'm taking the union of A and B, and then after taking the union, let's say I take the complement of the result. Okay, so this is going to be equal to take the complement of A, take the complement of B, and then this union will turn into intersection. Okay, so that's the first De Morgan's theorem. Then we have the second De Morgan's theorem, similar to this. So A and B, and then instead of union, let's say I take the intersection of A and B, and then I take the complement. What this will do is, you take the complement of A, and you take the complement of B, and this intersection will turn into a union. All right. That's the De Morgan's law. So I'm just giving this because this could be useful in some of the problems which we can solve. Okay. And finally, one last result, and that is if A is a subset of B, if A is a subset of B, then B's complement will be a subset of B's complement will be a subset of A's complement. Okay. I'll leave it to you. Okay. To verify this for yourself. Okay, please do that at home. All right, everyone. So I think I'm going to stop here. Next class, I will give you some fundamental laws of probability. These are your foundations. Okay, before we launch ourselves into probability, these basic ideas from set theory. This will be the foundation. Okay, so next class, what we'll do is that is tomorrow's class. I will introduce probability to you, and I'll give you some of the axioms, the basic laws of probability, which are also called as the axioms of probability. So this is what we will do, and then I'll introduce you to a very interesting concept called as the conditional probability. Okay, and conditional probability and something called as the Bayes theorem. These are very important because using this conditional probability and Bayes theorem, you will be able to understand some of these, what's happening, like because of COVID, some of the statistics that you're able to see moving around on, let's say, some news reports and so on. You will be able to understand those statistics much better by using this concept of conditional probability and the Bayes theorem. So this is something that we will do in tomorrow's class. All right, everyone. So